Okay, this is Andrew. We're going to do a quick presentation on IPv6. There's a lot of information out there about IPv6, but this is going to be pretty specific about how to address your network using IPv6. Um, also, well, let's go ahead and take a look at generally, I don't like to use metaphors when teaching network engineering courses, but this one is such a good metaphor and it's used so commonly that I'm going to go ahead and present it here. Okay, so it's the zip code and house number to IP address concept. Okay, so basically, if you look at this, each color here is a zip code. So this is 98121. This is a post office and this is a post office. So basically, these are intersections, and then these are like streets, and then these are houses on the streets. Okay, so you can see in the zip code 98121, there's houses. Okay, and these houses 98121-1, 98121-2. That's the first house on the street in this zip code. That's another house on the street in this zip code, and same thing down here in the 98122 zip code. We have 98122-1, 98122-2, and then the same thing over here. So the idea is, if I'm at 98121-1 and I want to send some mail over to 98122-2, well, it goes up here to the post office, and that zip code is right here in this post office. They know exactly where that zip code is. They send the mail over to the house. That's no problem. But if I'm at 98121-1 and I want to send mail over to 67121-1, well, this could be, for example, 5 states away. It could be a long way away. So what happens is he sends the mail up to the post office, and then the post office says, oh, well, it's going to have special instructions because they have no one what 67121-1 house is. So they just have special instructions, and the special instructions are, okay, just send it to the post office in the 67121 zip code. So that's what they do. They send it to the post office, then the post office sends it to the house. And then that's really exactly what's going on. It's what's going on in the IPv4 address. And basically, if you look at this green, is one network, right? And that's the 192.168.1.0 network. The red is another network. That's the 192.168.2.0. The 192.168.1.1 is the first PC on this network. The .2 is the second PC on this network. The .3 is the third, on up to how high can we go? Well, let's go back and look. Okay, here's a /24 network, okay? /24 means the first 24 bits are used for the network, and you can't change them, okay? They're network bits. And since this is 32 bits long, then the last 8 bits are what you're able to change. And you can change these all the way from 0 to 255, okay, in binary steps. So it gives you a total of 256 values, which 2 to the 8 is 256 because it's 8 bits. So if you remember from previous lecture, you can't use 0 because it's the network address, and the lowest one. You can't use the lowest one because it's the network address, and you can't use the highest one because it's the broadcast address. Don't worry about what the broadcast address is right now. Just know you can't use the lowest and the highest for an IP address. Okay, that's why here, see, this is the lowest, the 0. So the next one I can use for an IP address. So if this is /24 network, where do I stop? I have to stop at 254, even though there is a 255, but I have to stop. So if I have 260 computers and I want to put them on this network, it's a /24. I'm just out of luck. I mean, there's not enough space. Conversely, if I have only on this 192.168.2.0 network, I only have two computers, dot one and dot two. Well, also, I do have an address here, which might be dot three. Don't forget that the interfaces of your routers get IP addresses, but not of your switches, at least for layer two. Okay, so yeah, we have the opposite problem here. We only have two computers. How many addresses do we have? 254, so we wasted 252 addresses. So that's when we came into subnetting, which was basically increasing the value of the network bits to make our space a little smaller so that we could divide. Instead of having 256 here, we just divide it out. Maybe you can put like 128 here and 128 here, or you can divide it even more. You can do 64 here, 64 here, 64 here. You get the idea, and then just only use one network address, and then you're wasting less space. We've been through that. Okay, but all these, so we have this great IPv4 addressing scheme. Why do we need to go to IPv6? I mean, why? Well, basically, if you look here, this is 32 bits long, 8 times 4. And 2 to the 32, according to this, is over 4 billion possible unique addresses. So you think you have a phone at work, you have a computer at work, you have your cell phone, you have your tablet, you probably have 1, 2, 3 computers at home. It's possible each person has 5 to 10 IP addresses, and there's 7 billion people on Earth or something. Is 4 billion enough addresses? No, absolutely not. When they first started the internet, back in the 60s or whatever, it was just a few universities, and 4 billion seemed like certainly enough, so it wasn't. So they came up with these hacks like private addresses and NAT, and that's kept us limping along for the last decade or so, couple of decades. But what's happened now is they've just given the real solution, and that's IPv6. So let's take a look at just how much bigger IPv6 is. Okay. Well, here you had 32 bits on the IPv4. Well, let's take a quick look at IPv6. IPv6 is 8 hexbits. 1, 2, 3, 4, 5, 6, 7, 8. And each hexbit has 4 hexadecimal numbers in it. Now, a hexadecimal number has 16 values, so it takes 4 bits to represent one hexadecimal number, so each hexadent has 16 bits. And 16 times 8 hexadents is 128 bits. And this is 32. So basically, as a rough estimate, you're looking at the 4 billion. That's 32 times 4 billion times 4 billion, whatever. It's just huge. I mean, it's just so huge. Nobody even knows the name of this number. Okay, it's so huge. So we don't have to worry about running out of IP addresses anymore, but we have to learn how to use IPv6. And even a bigger problem is a lot of companies, they'll grow, and they already have IPv4, so now they're growing and they use IPv6, so you've got a mixed environment, and you have to create tunnels and such that go back and forth from IPv4 to IPv6, which is beyond the scope of this presentation. Also, this presentation is not really about converting back and forth for hex numbers to binary to decimal, but we're going to do a quick review or overview of what a hex number is. A hex number just is what you need to know to get through the rest of this assignment. So you can see the hexadecimal goes from 0 to F, and it has 16 values. The first 10 correlate, or 11 here, the first 10 correlate with the decimal 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 6, 7, 8, 9. And then when you get to 10, it's A, B, C, D, E, F. And then the binary is just 0. This is your 1's place, 2's place, 4's place, 8's place. So this is 1. This is 1, 2, which is 2, 1, 2, and 1, 1, which is 3, 1, 4. 1, 4, and a 1 is a 5. A 4 and a 2 is a 6. You get the idea. So let's look at the hexadecimal number then. So just like in decimal, you have, this is your 1's place. This is your 10's place. Then 10 times 10, this is your 100's place. 100 times 10, this is your 1,000's place. Each time you go to the left, you go up 10. That's why it's called decimal. Well, here, each time you go to the left, it goes up 16. So it starts at your 1's place right here, and then your 16's place, and then 16 times 16, which is 256, and then 16 times 256, which is 4096. So if you have this hexadecimal number F2A5, well, 5 times 1 is 5. 16 times A, which is 10, is 160. Okay, 256 times 2 is 512. And then if you go here, F is 15. Okay, 15 times the 4096. So you total all this up and you get a number here. And this number, this is now a base 10 decimal number. Okay, so you get the idea. Like I said, this is not for right now. If you need to convert between hexadecimal, decimal, binary, and you don't feel like you have enough practice, just get an online calculator and do it. So let's take another quick look here at the IPV6 example. Again, we've discussed that this is a hextet, and there's 8 of them. Okay, now if we look inside one of these hextets, it's comprised of these 16 bits. Okay, so it takes 4 bits to represent one hex number. So what's this? Is 1's place, 2's place, 4's place. You have 1, 4, that's 4. So what's this? Is 1's place, 2's place, 4's place, 8. So 8, 12, 13, 14. That's an E. Okay, 8, remember, is a 10, so that's 8, and a 2 is a 10. And then this is a 0. All right, so looking at this, what's a potential problem with this is, I mean, look just how huge it is. You know, it's just huge. So they've come up with some rules to compress an IPv6 number. The thing is we compress the number for humans, for us, to make it easier to type in and memorize, things like that. But the computer has to see that 128-bit number. So any rules we do to derive at some reduced compressed set needs to be able to be undone to get back to the original number. So we're going to look at that, and it's IPv6 0 compression and lead-in 0 compression. Okay, so basically the question is, here's the number. Let's say here's the IPv6 number, and we want to compress that, and we're going to do that by just eliminating strings of zeros. So if I get rid of these 2 hextets of zeros and just replace it with a colon, how many hextets do I have left? 1, 2, 3, 4, 5, 6. So the question is, can you rebuild it? If I give you this number and I say, get this back to a real IPv6 number, you can rebuild it, because you know there has to be 8, so you know there's 2 hextets of zeros missing in between these colons. Okay, now if I put these colons, I had 2 sets of colons and got rid of this 2, could you rebuild it? No, because you would then have 5 hextets, right? 1, 2, 3, 4, 5, and you know you need 8, but you wouldn't know if 2 hextets go here and 1 goes here, or if 1 goes here and 2 goes here. So you just wouldn't know. You couldn't rebuild it. So if all you got to remember is you can only use this colon representation one time. All right, next is leading zero compression, and it is just what it says. You get, if the lead, any numbers that are leading, you can just, or zeros, you can get rid of them. So look at this hextant, the 06B0. You can get rid of the 0. Look at this one, the 005B. You just get rid of the 00. And then you have 4 zeros, you can actually get rid of 3 of them. So you get the idea. You just get rid of the leading zeros. And then if I give you this number, can you rebuild it? Yes, you know there has to be 4 here, and you know there have to be zeros. So you put 1 here, 2 zeros here, 3 zeros here, 1 0 here, and you can rebuild it. So the question is here, let's just mix them together. So basically you have the same thing. We used our colon right here to get rid of these 2 hextants, and then we used our leading zeros to get rid of all the leading zeros. So the idea is here, I now have this reduced number that I can type into computers, and not this one in particular, but if certain ways you can work these out, you can get them to where it's easy to remember them, whether as a human, where there's no way you could really remember them as a full IPv6 address. But the computer can fully follow these rules and rebuild the number that it needs to see. Okay. So that's great, and we looked at an IPv6, IPv4 network, right? We did that. So how do I use that to actually address my network using IPv6? So I removed the IPv4 addressing, right? And now we're going to try to come up with IPv6 addresses to put on that network, the same network. So the IPv6, what gets masked, okay? In IPv4, the address comes with a mask, right? It's going to be like a /24. We saw that. IPv6 uses subnets, but the subnet ID is built into the address. So the first 3 hectants, which are the first 48 bits, are the network prefixes. Okay, those are network bits. And then the next 16 bits, which is the 4th hextant, are subnet IDs used for defining subnets. And then the last 64 bits, that's just your device ID, which is, you know, IP addresses you assigned to your device. So we look here, you have 1, 2, 3, 4, 5, 6, 7, 8. So we have to figure out how to modify this 4th hextant such that we can break this network into subnets, just like we did in an IPv4. But the process is similar, but just a little different. So let's say I have the number and I want to break it into 64 subnets. Well, 2 to the 6 is 64, right? So I need 6 network bits. So that's 1, 2, 3, 4, 5, 6. So I have to take, out of the 16 bits in the 4th hextet, I have to take the first 6 bits, okay? And I have to make them a 1 because they're network bits or 1s, right? Okay, so now I have to just rewrite this binary number into hexadecimal. You can use a calculator to convert it, but look at the first 4. The first 4 represents, remember, each one of these numbers has 4 bits represented in it. So that this is 0, that's 4 zeros. The second one is 0, it's 4 zeros. So after that, we see we have 0, 0, 1, 1. Okay, well, 1, 1, 0, 0. So that's 1's place, 2's place, 4's place. So we have 1, 4, 1, 8, which is 12, which is a C. 10 is A, 11's B, 12's C. Okay, and then we saw that F is all 1s, right? Which is a 15. 1, 2, 3, 4. So you see, basically what we did is in this 4th hextet, we just added the number of network bits we needed to subnet the network into as many subnets as we need. Okay, so let's take a look at another example. That was kind of a high level. We're going to get a little more detail here. So, and all this is like you do need to know how to do this eventually, but right now it's like, how you have a math class and the professor goes through all this to derive a equation, and then you just use that equation to solve a problem. Well, that's basically what we're doing here, okay? We're going to derive networks, and then you'll use those networks in the assignment but you need to be able to do this eventually, okay? So the slash just indicates the bits that are fixed. We discussed that, okay? IPv6 is 128 bits long. So your network as organization assigns you basically 128 minus the prefix length value. So if we had 128 bits total and this is what we can't touch, 48, then 80 is what we can touch. It's just like in the IPv4, it's just more bits, right? So 80 is what we can use. Okay, but the importance of the slash is to recognize that this, it's like the boundary of your network. I mean, it's the number you're assigned where your network starts and where your network ends. So that's really telling you the space you have. Okay, so when we did subnet masking in IPv4, it's the same here. To find the lower address, just and the higher address, just or. And that gives you the top, the low address and the bottom address, and then in between those is what you have for the addresses you can use. Okay, let's look at an example then. So if we write this, so this is still the same IPv6 address, this 48. Let's write it in binary. So remember, each one of these hex gets 4 bits. So that's 2 is 2, 001, 001. You should have that by now. DB. So this is really 0 dB8. Don't forget your leading 0. 0 dB8. That's a 1, 2, 4, 8 place. 1, 8. So 8, 1, and 2 is what? 11. That's B. So you get the idea. So all of these fill in. Here's your 1, 2, 3, and 4. So basically, we just write this hex number out in binary, right? So now let's say, for example, I have to have, out of this is what I bought, I have to have 4 subnets, because this gives me only one network, but just incredible amount of host IP addresses, but only one network. So I have to break it in. I have to use those 80 bits I have over here. I have to use some of them for more networks. So that's what I'm doing, is I'm taking 2 more bits. Let's say I'll take 2 more bits because I need 4 networks. Binary 2 gives you how many? You have 2 can give you 4 combinations. So 2 to the 2 is 4. So anyway, let's go ahead. We already wrote this out, but now here's the end of your 1, 2, 3, 4, right? So here's the end. Now this is where the slash is coming in, okay? So if I want to borrow 2 bits, that means there's four cases, right? 0, 0, 0, 1, 1, 0, and 1, 1. That's the only cases I can have with these 2 bits, right? And then all the rest are zeros, okay? So let's go ahead and look here. So these 4 bits form a hexadecimal number, if you remember, right? So this 4 bits forms the first hexadecimal number in the 4th hextant right here, because 1, 2, 3, 4. We're in the 4th hextant. This is the first hexadecimal number. So what's this in a hexadecimal number? 0. So you see right here it's 0. So what's this and a hexadecimal number. That's the ones place, twos place, fours place. This binary is a 4, right? So you see it right here as a 4. So what's this in a hex number? That's 1, 2, 4, and 8's place. So that's an 8. So that's an 8. And then this is a C, which is 12, 8 and 4. So that puts you here, C. So now you have these 4 networks you can use, right? And you can go ahead and use these on your project. So these are your IPv6 networks you can use, and then just in this space here, you would put 1, 2, 3, 4, 5, on up to whatever you need, just like you can see it here. So it would just be 1, 2, 3, 4, and then this would be the 4,000, 1, 2, 3, 4, the 8,000, 1, 2, 3, 4. You get the idea. So you have these 4 subnets that you can use to subnet your network. Okay, so basically I just did it for you. So here's a network right here, right? Which is the 0000/50, which we just came up with. Well, here's the number 1 house, or the number 1 PC on that network. Here's the number 2 PC on that network, the number 3 PC on that network, on down to however many we need, which I think the project said 120. And then this is the same thing. The red is, don't forget to give your router's IP addresses, the router interfaces. So, one of these would go to the router interface, which would be, like 100 or whatever. Just put it on there. So here's another network, the 4,000, and then you can see there's the first PC1, the second PC2 on that, and then this network would be the same thing. Okay, great. So I think that should be getting cleared up quite a bit now. So let's start to take a look at the static routes. We did static routes for IPv4, so we need to do them for IPv6 as well. So let's just pull out this section just to look at the static routes, just to make it a little cleaner. Okay, so we just pulled out that little section. So again, if I'm on this PC, I can't. This router doesn't know about this red network because it's not attached to it. So it has to have some special instruction to know how to get there, and that's either a dynamic route or a static route, but we're going to use static routes for now. So basically I have to tell this router how to reach this red network over here, and the way you do that in IPv6, the command is just IPv6 route network you want to reach, which is the 4,000. Okay, but don't put the IP address, it's the network. And then the next hop. Okay, the next hop, if you're on router 1, the next hop is right here. So it's going to be whatever you labeled that, the 8001. If you made that interface 8001, and this one the 8002. So this is the way we're going to do it. You could use FE80. There's, the problem is people spend decades learning all this stuff about networks, so there's always more detail we could do, or just like when you're learning switches or layer 2 for CCNA, and then as soon as you get to CCNP they tell you, okay, switches are layer 3. There's a lot of that going on here. We're learning things a step at a time. There are a lot more details, but this is what we're doing for now. Okay, so with that, I'm going to maybe not change it. Okay, this is for other classes that are watching this video. This is for the IS38 Project 1 only. The network is going to be changed slightly, and the only change is we're taking the phones out. So initially I thought you might want to include a CUCM server and routes using that, but we're going to just drop that for now. So just use your 120 PCs, your 60 PCs, and then your 25 servers, okay? So then what you need to do for the whole project, this is it. Subnet everything for IPv4, which really has been done for you. Define your pool for DHCP and say, okay, on my DHCP server here, I'm going to put my pool of addresses. So for the 192.168.1.0 pool, it's going to be from 1 to 120. And then for the 192.168.2 pool, it's going to be blah, 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 whatever it is. And then put your static routes. So put your static routes that allow computers on this network to reach these, and then put static routes which allow these networks here, these PCs on these networks to reach these. And then also the description of the problem is to put static routes to reach the outside internet. So do that. And then you're done with IPv4, and then just do the same thing over again with IPv6. So we discussed in a real, so I had future growth. I wanted you to kind of mix IPv6 and IPv4, but we're just going to get rid of that. We got rid of that. So, yeah, just do it over again in IPv6 addresses, which we just went through just now, and then use your IPv6 statics routes, do your IPv6 DHCP pools, and then do your static routes to reach the internet, and you're done. All right, so I hope that helped you out a lot, and let's go ahead and get this project in because we've got other projects to get onto. All right, thanks.